What would you build if you never had to launch it? Imagine constructing a satellite dish the size of a football field, not on Earth, but directly in orbit where there's no gravity to fight. Engineers at MIT have developed a framework that could make this possible by figuring out exactly which materials and methods work best for manufacturing in space. For decades, the size of space structures has been limited by one brutal constraint: everything has to survive launch. That means folding, compressing, and reinforcing, all adding weight and complexity. The largest deployable reflectors today top out around 35 meters, but next-generation applications, continuous climate monitoring from orbit, megawatt solar power stations, even solar sails for deep space, demand structures 10 to 100 times larger. Previous attempts at building in space have stalled. Welding requires enormous energy. Additive manufacturing is slow, and no one had systematically compared the options. Engineers were choosing processes based on intuition, not data. Without a rigorous engineering framework for comparing materials and processes, the dream of 100-meter space structures remained exactly that, a dream. The MIT team took a fundamentally different approach. Instead of testing one process in isolation, they built a systematic framework for evaluating every candidate material and manufacturing method side by side. They identified three critical material properties. First, thermal stability, how much a structure bends when one side faces the sun and the other faces deep space. This is measured by the ratio of thermal conductivity to expansion. Second, resistance to disturbance loads. In orbit, even tiny accelerations from attitude control can cause vibrations. The ideal material combines high stiffness for fast natural frequencies with enough internal damping to absorb disturbances, a trade-off most materials can't satisfy. Third, buckling strength per unit mass. Longer struts in larger structures are more vulnerable to buckling. Materials with high specific stiffness, the ratio of stiffness to density, let you build large without adding weight. Then they compared manufacturing processes on two metrics: energy consumption and accuracy. Melting metal in space requires around 8 megajoules per kilogram. Extruding composites needs about 5, but deformation processing, simply bending metal into shape, uses less than 2. That's the key finding. Bending metal is dramatically cheaper in energy than melting or curing it, and because no heating is involved, thermal distortions during fabrication are essentially eliminated. The result is a complete decision framework: which material, which process, and why, backed by physics. The analysis revealed surprising trade-offs. No single material wins on every metric. Carbon fiber composites are lightest and stiffest, but they have poor passive damping. Invar has excellent thermal stability, but it's heavy. Each material excels differently. For the case study, they designed a tetrahedral truss to support a 100-meter reflector. With deformation processing of Invar, the entire structure could be built in roughly 1 day. Extrusion of carbon fiber composites? Nearly a week. Melt-based additive manufacturing of aluminum? Up to 50 days. The energy difference is enormous. At 1 kilowatt of spacecraft power, bending Invar wire into a truss is more than 50 times faster than 3D printing it from aluminum. Their simulations also quantified accuracy challenges. Extruding carbon fiber composite tubes into space creates temperature and curing gradients that curve the structure. Higher nozzle temperatures reduce this distortion but can't eliminate it entirely. Deformation processing avoids these thermal problems entirely. Its main accuracy challenge is elastic springback, the material bouncing back after bending, which is well understood and can be compensated with calibrated tooling. This framework changes how engineers approach space construction. Instead of defaulting to 3D printing, the most hyped approach, teams can now systematically select the optimal material process combination for their specific mission, whether it's a reflector, solar array, or truss boom. For the space industry, deformation processing of metal wire is a standout result. It's low energy, fast, accurate, and compatible with materials like Invar that have excellent thermal stability. Exactly what precision space structures need. Challenges remain. Connecting structural members in space, handling materials with low ductility, and developing hybrid feedstocks that combine the best properties of metals and composites are all active areas of research. The next giant leap in space won't be about going farther. It will be about building bigger. And thanks to this work from MIT, we now know how to choose the right tools for the job.